Hello. Okay, so maybe we can start with the second session of day 2. The chair of the afternoon session is Shayantan. Over to Shayan.
Hi, welcome to the post-lunch session. So first, for the first half of the session, we have 2 talks. The first talk of this session is by Jae Sung Lee. He'll be telling us about thermodynamic trade-off relations. Yeah. Okay, so I'll remind you.
35 minutes left.
Yeah, talk is 40 plus 5.
Okay.
So 40.
35 is okay. Okay, thank you. Okay, so can you hear me? Okay, thank you. So thank you for introduction. And first of all, I'd like to thank the organizers, Pinaki and Arna, for this kind invitation. Okay, so today I'm going to talk about some important thermodynamic trade-off relations observed in stochastic system. So this is a schematic diagram of a stochastic system I'm interested in. So here, t equals 0 is initial time, and tau is final time. So the system starts from initial state x1. And here x1 prime is, let's say that this is a final state. So this gamma 1 is some single stochastic trajectory of a system. Okay, so system can start from many other different initial state. So this initial state constitutes this initial distribution P0, and final states are final distribution P tau. So in this setting, we are interested in measuring some observable theta. Theta is a function of gamma trajectory. So heat, work, and displacement are examples of observable. And one special observable is entropy production, which is also a function of trajectory. So with this setup, question is there any general relationship between the entropy production and other measurable quantities? So for this question today, I'm going to talk about mainly 2 subjects. So the first one is thermodynamic uncertainty relation, and shortly saying TUR. So in this morning session, Professor Ian also talked about entropy production measurement by using TUR. And the second part is about the speed limit. Okay, so let me begin with the first part. Okay, so TUR is a relation between entropy production and fluctuation of observable. So it looks like this. So this is a variance of an observable, and this is average value of observable. So this is average value of entropy production. So their product, this term, left term, is usually called relative fluctuation. So their product is larger than some universal constant. Here Kb is Boltzmann constant. So let me give you an example. So this is a movie for molecular motor. So here let's take the observable theta as a displacement of this molecular motor. Of course, because of this stochasticity, this x variable is also stochastic variable, so it has a finite variance. Okay, so here, if we want to reduce this relative fluctuation, then from this inequality, entropy production should increase. Or if we want to reduce this entropy production, then relative fluctuation should increase. So this is a kind of a trade-off relation. We have to pay more thermodynamic cost for reducing fluctuation. This is the meaning of TUR. And if we rearrange these inequalities, then we have this. Then thermodynamic second law just telling us that entropy production is larger than 0. But TUR is telling us that entropy production is larger than some positive number. So it gives a stronger bound than the thermodynamic second law. So this is a fundamental importance as in a theoretical aspect. Okay, so TOR was first discovered in 2015. And it was first proved in 2016 by using large deviation theory. And after that, 2018, it was also proved by generating function method. And in 2019, it was finally proved by using Cramér-Rao inequality. And this Cramér-Rao inequality is a famous inequality in information science. So it looks like this. So here there is some parameter epsilon. So epsilon is some kind of estimation parameter. And here I is called Fisher information. Because this inequality greatly simplifies the TOR derivation, so in my talk, I will only focus on this Cramér-Rao inequality derivation. Okay, so let me first relate this Cramér-Rao inequality to our stochastic system. Okay, so let's suppose that we have this original dynamics over Langevin dynamics. So here F is a given external force. Now here we add some perturbation force. So we can regard this epsilon parameter, here epsilon parameter as a perturbation parameter, small number. So if we take epsilon goes to zero limit, then this perturb dynamics goes back to the original dynamics. Okay? Okay, so in such a way we can relate this inequality to our stochastic system, to the perturb dynamics. So here, at the epsilon equal to zero limit, we can evaluate this inequality, and let's compare these two inequalities. This is a Cramér-Rao inequality in the original dynamics, and this is a TOR. So you can see the similarity, right? So if these three equalities are satisfied, then actually these two inequalities are identical. So, and the first part, the first equality is actually automatically true. So, if we can show these two equalities by using some proper function of perturbation force, then we can derive this TOR by using this inequality. This is a basic strategy to show TOR by using Cramér-Rao inequality. Okay. So the remaining thing we have to do is we have to find some proper perturbation force which leads to these two equalities. So what kind of perturbation leads to these equalities? So probably I think that there can be many possible ways, but one of the most intuitive one is like this. So here, this one is an observable average in the perturbed dynamics. And this is an average in the original dynamics. So between them, if there is this kind of a relation, then the first equality is satisfied, right? So what kind of perturbation leads to this relation? So from now on, for simplicity, I will only focus on a steady state. So in the steady state, let's say that this theta dot average is a steady state average rate. Then the time accumulated observable average is simply given by rate times total time tau. Okay, so here I will make a time scaling perturbation. So it is simply given in this way. So we just scale time with this factor, 1 plus epsilon factor. Then the total time, so this tau is a total time. So total time is also scaled by the same factor. Then the accumulated observable is also scaled by the same factor. So, which means that this time scaling perturbation gives this relation, then the first equality is satisfied. So the remaining thing we have to check is that whether this scaling perturbation also leads to this second equality. Okay, so let's check it. Okay, so this is the original dynamics, and this is a corresponding Fokker-Planck equation. And in the status, okay, so here we make a time scaling perturbation. So 1 plus epsilon factor here, and this factor comes from this time derivative. And here, steady state, it becomes 0. And this part is a probability current in the original dynamics. So if we rearrange these terms, then we can show this. And then this g of x function is defined in this way. So let's look at this Fokker-Planck equation. This is a result of this time scaling perturbation in the steady state. Then actually this Fokker-Planck equation is equivalent to this perturbed dynamics Langevin equation in the steady state. So which means that this time scaling perturbation is equivalent to this perturbed dynamics in the steady state. Okay, so now we know the form of g of x perturbation force form, so we can evaluate the Fisher information. So this is a definition of Fisher information. Here, P is a path probability for this perturbed dynamics. So we can easily calculate this Fisher information, and the result is really, it gives a entropy production divided by 2 kb. So it means that we started from time scaling perturbation, and it satisfies these two equalities, so we finally derive TUR. Okay, so this is the simplest way to derive TUR as far as I know. So this TUR is, okay.
Sufficient, Kramer-Rao is looking for an inference problem.
Yes?
Is the inference here basically inference of epsilon?
Not the epsilon, but in this formulation, epsilon is just some perturbation parameter. To make
the underlying inference problem that.
Yes, originally the Kramer inequality is about estimating the estimation parameter, but here we apply this inequality to perturb some original dynamics. That's just a mathematical, treatment. But because the Kramer inequality is very general, inequality for it is satisfied for any probability distribution function, so we can apply any system. Okay, so this TUR is valid for this overdamped Langevin system and continuous time Markov jump process in the steady state. So if the system is not in the steady state, then some modification is necessary. So there is a sum operator here, but we can easily check that this expression is reduced to this overdamped TUR in the steady state. Okay, so this TUR is valid for a system with even parity variables under time reversal. So here, even parity means that, for example, position is even parity variable under time reversal. So for example, in overdamped Langevin system, there is only position variable. But then what happens for a system with odd parity variable? So here, odd parity variables means, for example, velocity or momentum variable. So such a variable is in underdamped Langevin dynamics. So the question is that this TUR is also valid for such an underdamped system. Okay, so let's check it with a concrete example. So the example is Brownian particle in a magnetic field. So this is underdamped Langevin dynamics. So there is a velocity variable here. So this is an inertia term, and this is a dissipation term, and the particle is trapped in harmonic potential, and this one is a non-conservative force. And this B is magnetic field, so this is a Lorentz force, and this is a thermal noise. So this is a two-dimensional motion. Okay, so here we are interested in measuring work current. So this work means that work done by this non-conservative force. This is actually the rotating force. So because this is a fully analytic model, so we can analytically calculate this variance, observable variance, and this average of that, and total entropy production. So we can analytically have this Q factor. So if TOR is valid for this system, then this Q factor must be larger than 1 for any parameters, right? Okay, so let's check it. So here y-axis is a Q factor, and x-axis is some parameter, actually the magnetic field. And these many dots are Q factor evaluated from various parameters of this model. And this TOR bound is this one line. So as you can see from this plot, then there is some region where this TOR is violated. So it means that TOR is not satisfied for underdamped Langevin dynamics. Okay, so let me summarize in this way. So this TOR is valid for even parity variable system. Then what is a TOR for underdamped Langevin system? So I think this is an important question as an intermediate step to go further to the open quantum system TOR. Recently, many people are also interested in TOR for open quantum system. And as you know, the quantum system intrinsically has a momentum operators, which is a time which has odd parity under time reversal. So I want to establish a consistent theory. What I mean by consistent is that like this. So let's suppose that we know the expression of this quantum system TOR. Then if we take how bar goes to zero limit, then we expect this expression is reduced to this underdamped TOR. And here, if we take m goes to zero limit, which is overdamped limit, then we expect this underdamped TOR is reduced to this overdamped TOR. This is what I mean by consistent. So the goal of my research is to find this consistent underdamped TOR expression. Okay, so for doing this, 4 years ago, I used the same technique, time scaling perturbation. I applied this technique to the underdamped Langevin system, and finally I obtained this inequality. Of course, there is some similarity between this is original overdamped TOR, and this is a new inequality, but there is some difference here. But actually, even though we obtained this inequality, but it has some problem. So the first problem is that it contains not measurable quantities. So it is hard to apply this theory to experiment. So, and the second problem is that this inequality gives a loose bound. So this is a previous example, Brownian particle in a magnetic field. So here, these red dots are evaluated by using this overdamped TOR, and these blue dots are Q factor evaluated by using this new inequality. And this line is a TOR bound. So as we already saw, if we use this overdamped TOR, then there is some region where TOR is violated. But if we use this new inequality, then you see that these blue dots are always above this TOR bound. So it means that this inequality holds. But the thing is that the y-axis is a logarithmic scale, so the minimum value of the blue dots is much larger than this lower bound. So it means that even though it is true, but it gives a loose bound. So it is not actually practical. The third problem is that if we take m goes to zero limit, it is not reduced to this overdamped TOR. So it means that this time scaling perturbation is not a consistent perturbation in the underdamped Langevin dynamics. So then what is the consistent perturbation? Okay, so I finally found the consistent perturbation. So okay, so let's say that this is the original underdamped dynamics. and this is a corresponding Fokker-Planck equation. So this is a Fokker-Planck operator, and this can be divided into two parts, reversible part and irreversible part in this way. And here we put this scaling factor only in front of this irreversible operator, not this reversible operator. And we can check that if we take m goes to 0 limit, this underdamped Fokker-Planck equation is reduced to this overdamped Fokker-Planck equation. And this overdamped Fokker-Planck equation corresponds to this previous expression of the time scaling perturbed Fokker-Planck equation for overdamped Langevin system. So that means that this perturbation, it looks strange, but this is a consistent perturbation, gives this consistent theory. So finally, anyway, we evaluate this Cramér inequality by using this perturbation, and we have this Fisher information is given by this way. So indeed, it gives a total entropy production, and there is additional term here, so it is related to initial Shannon entropy. But this Shannon entropy term is time-intensive quantity, but this entropy production is a time-extensive quantity. So in the long time limit, this can be neglected. So Fisher information really gives the entropy production. Okay, so this is a new TOR, underdamped TOR we obtained. So it has three advantages. So the first one is it gives a tight bound. And the second is it is experimentally accessible when all forces are known and controllable. And the third one is it is consistent with the overdamped TOR. So when we take m goes to 0 limit, then this expression is reduced to the original, overdamped TOR. So let me show you an example. So the same example, previous one, so Brownian particle in a magnetic field. So because this is an analytic model, so we can evaluate this Q factor. And this is the result. So this is a y-axis is a Q factor, and x-axis is the same magnetic field parameter. And this line is a TOR bound. So as you can see that many dots are actually tightly bounded by this inequality. So it means that it gives a tight bound compared to this previous one, and you can see the tightness. Okay.
So this entropy production which you are writing here, this is both considering position and velocity together?
Yes.
So you have to write the action for both of them, right? In the
Yes,
joint
right.
phase space?
Yes. Right.
And then from there you have to take the ratio between the forward path and the reverse path, and then you define the entropy production.
Yes, right. Yes.
Okay, thanks.
Okay. In the underdamped dynamics, yeah. Okay, so this is a summary of the first part. So TOR is a kind of a trade-off relation. So we can derive TOR by using time scaling perturbation, but for underdamped system, we cannot do that. So we found a consistent perturbation scheme and derive a tight and experimentally accessible TOR for odd parity system. Okay, so let me move to the second part, which is about the speed limit. Okay, so speed limit is a relation between now entropy production and the initial and final distributions. So let's suppose that we have initial distribution and final distribution, and we want to move this initial distribution to this final distribution during the finite time tau. Then this inequality holds. So this is called the speed limit. So here tau is transition time, and this is entropy production, and this dTV, this is a statistical distance between two distributions, P and Q. So here, two distribution means initial and final distribution. And this A bar is called dynamical activity. So I will explain these two quantities later explicitly. Okay, so here, so for example, if we want to reduce this transition time, then from this inequality, entropy production should increase. Or if we want to reduce entropy production, then transition time should increase. So this is also kind of a trade-off relation. We have to pay more thermodynamic cost for faster transition. Okay, and conventionally we write speed limit in this way. So in this talk, I will only focus on a continuous time Markov jump process. So this is a master equation. So Pn is a probability of state n, and this is a transition rate from m state to n state. And in the Markov jump process, this is an expression for entropy production, but there is some star notation here. Star notation. So if we take this R star as some original rate, then this becomes the usual entropy production rate. But if we take R star in this way, then this becomes Hatano-Sasa entropy production rate. But in this talk, for simplicity, I will only focus on this usual entropy production. But anyway, this relation holds for these two entropy production rate. And A dot here, so A dot here called dynamical activity rate or number of jumps rate. And integration from 0 to tau gives a total number of jumps or total activity. And total activity divided by total time gives mean activity. So here, this quantity is actually mean activity. And the final one, this one, is the definition of this one is this. So it is called total variation distance. So it is a distance between two distributions, P and Q. So it is in between 0 and 1. So if the two distributions are exactly same, then it becomes 0. And when these two distributions are completely different, then it becomes 1. Okay, so it denotes the distance between two distributions. Okay, so and for simplicity, I will use a notation L, curly L, instead of this one, so we can simply write speed limit in this way. Okay, so this is a previous form of speed limit, but today I'm going to introduce some general form of speed limit. So what I mean by general is that this previous form is a special case of this general form. Okay, so to derive this general form, we need this key relation. So this means that there exists some function, convex function h, which satisfies this inequality. I will show you the explicit form of h function later, but at this stage, please accept this key relation. And then by dividing by the same factor, we have this inequality. And here now we define function g of x in this way. Then this left-hand side is nothing but this g function. So by taking the inverse function of g, then we have this inequality. And by using this definition of total activity, then we finally have this general form. So the remaining part to show this speed limit is to show this key relation. Okay, so let me explain how to derive this key relation. Okay, so this L, this is a definition of total variation distance. And it is tried to forward to show that L is smaller than this equation. Actually, this is easy to show that, and you can see the derivation in this paper. And here I will define two quantities, Q and Q tilde. So here Q is related to this part, and Q tilde is related to this part. And here A dot is activity rate, and here it acts as some normalized constant. So it means that this Q and Q tilde can be regarded as some kind of a probability. Okay, so by using this definition, we can rewrite equation in this way. And then the definition of a total variation distance is given in this way. So finally, we can write in this way. So here I will use some important properties of a statistical distance. So I mentioned that the total variation distance, this is the total variation distance, as it is in between 0 and 1. And this is also well-known Kullback-Leibler divergence. So this is a definition of, Kullback-Leibler divergence. And here, KL divergence is larger than 0, but it has no upper bound. It can diverge. And the important thing is that there is some relation between these two distances. So there exists some function h which satisfies this inequality. So this is well known in the information science society. So here I will use this inequality. I will show you the explicit form h later. Okay, so here I will use the inverse function of h, then we can show this inequality. And then here we can evaluate this KL divergence by using this definition. Then it is simply given by entropy production rate divided by activity rate. And one important property of Q and Q tilde is that this is a KL divergence of a Q and Q tilde, and this is the KL divergence of a Q tilde Q. So the order is exchanged, but in general, the KL divergence is actually, it is not symmetric, but in our case, Q and Q tilde, we can easily show that they are symmetric. So I will use this property later, so please remember this important property. Okay, so by using this equation, then we can rewrite equation in this way. And finally, by using Johnson's inequality, we have this. So L is smaller than this quantity, so we finally show this key relation. Okay, so because we showed this key relation, so this is automatically true, so we derive this general form. Okay, then I will show you the explicit form of h function. So one simplest one is a Pinsker function, which is given by 2x squared. So let me give you an example. So let's say that there are two distributions. This is a two-state model distribution. So P distribution is 0, 1, and Q distribution is 1, 0. Then we can easily calculate this total variation distance. It is simply given by 1, and KL divergence diverges. So by using these two quantities and these two numbers, and by using this h function, then we can easily check this inequality is satisfied. It is 2 is smaller than infinity. Even though this inequality holds, but actually very loosely hold. So it means that 2 is much, much smaller than infinity, right? So it means that this Pinsker function is very loose near d is close to 1. But Pinsker function is tight only when d is close to 0. So what does it mean? So actually we are now interested in these two distribution, Q and Q tilde. And Q distribution is like the forward reaction rate. And Q tilde is like a backward reaction rate. So the meaning of this, D is close to 0 means that two distributions are almost equal. It means that the forward rate and backward rate are almost same. It means that the process is nearly reversible. However, when D is close to 1, then it means that two distributions are very much different. So it means that process is highly irreversible process. So it means that if we use a Pinsker function, then this bound becomes very loose for highly irreversible process, but it is tight only for a nearly reversible process. Okay, so to enhance this tightness, we can use other functions. So for example, Bretagne-Huber function or Gilardoni function. then this is the plot of these three functions. So this is a h function, and x-axis is d. So d equal 1. Pinsker function is finite, but bh function and g function diverges. So in this, I mean, at this point, these two functions gives a much tighter bound compared to the Pinsker function. Okay. But if the KL divergence satisfy this this exchange, I mean, if these two KL divergence is symmetric, then we can use the tightest bound. So this is a tightest bound, and you can see that this pink curve is always larger than other three functions. So it gives a actually tightest bound. I will show you the example later. And as I mentioned, in our case, the KL divergence is symmetric. Q and Q tilde can be exchanged. So we can actually use this tightest bound. Okay, so for example, if we use this Pinsker function, then we have this previous speed limit form. But if we use this tightest bound, then we have this new speed limit. Okay, so and we can compare this. I mean, actually, recently, Andreas also derived the almost same inequality by using Wasserstein distance. Okay, so we can apply this speed limit to a finite time Landau's bound problem. So what is a Landau's problem? So it means that for erasing 1 bit of information, at least kBt log 2 heat should be dissipated. So this is a minimum heat is attained only in the quasi-static limit. So for finite process, some additional cost is necessary. So from the series of studies, this one is known as proportional to 1/tau. So when tau goes to 0, quasi-static limit, it goes to 0. Additional cost goes to 0. Okay, so then the erasing process is like this. So let's suppose that there is the binary state memory here. So it has a 2 state, and in this example, the system is located at the 0 state. So we read this memory is in 0 state. And let's suppose that there are many memory, and then initial distribution is observing 0 state is half, probability is half, and probability for observing 1 state also half. So let's say that this is the initial distribution, and erasing process is nothing but a reset process, reset to 0 process. So after erasing process, all memory state is 0. So the final distribution is 0 probability equal to 1 and 1 probability equal to 0. So the erasing process is nothing but the distribution change from initial state to final state. So we can simply calculate the total variation distance in this case, which is 1/2. And also we can calculate Shannon entropy change, which is minus log 2. And this is our speed limit, and we can rearrange it, and then we have this one. And entropy production can be divided into Shannon entropy term and heat dissipation. So finally, we have this inequality, and this is nothing but a finite time Landau's bound, and this term means additional cost. So for example, if we choose Pinsker function, then this additional cost is proportional to 1/tau. This corresponds to the previous study. But if we use this tightest bound, then we have new additional cost bound. So let me give you an example. So this is a discrete 1-bit model. So it has only 2 states. And now let's say that initially the system is a 1 state. And by raising the energy state of this, and we can move this particle to this one. So in such a way, we can erase the memory. So from this model, actually these many dots are evaluated from this model for various parameters. So y-axis is entropy production, and x-axis is inverse of V. And the thing is that when v equal to 1, this line is this area is a very highly irreversible process regime, and this is a nearly reversible process regime. And this orange line is a Pinsker function bound, and this blue line is a tightest bound, symmetric KLD bound. And this is a magnified view of this plot. And you see that this is a data point, and this blue curve is really tight. Actually, it touches the bottom of the data point, but this Pinsker function is here. And you see that this blue line diverges at this v equal to 1 point, but Pinsker function is finite, so it means that Pinsker function is infinitely loose bound compared to the tightest bound near this highly irreversible regime. And we also found some sufficient condition for optimal protocol, which is along this tightest line. Okay, so and even though I started from this Markov jumper process, discrete state, but we can also apply to this continuous model. So this is a data for a continuous model, and you can see that it is also bounded by these equalities. Okay, so this is summary for the second part. Okay, so because I'm running out of time, so this is my final comment on we recently studied the thermodynamic trade-off relation in the stochastic resetting process. So the stochastic resetting is a strategy for boosting the speed of a target searching process by using random walk. So it consists of a sequential of a random walk and instantaneous reset, random walk, instantaneous reset, and finally it reaches the goal here. So this is a stochastic resetting process, but as I mentioned, the reset process is an irreversible process. So it must incur thermodynamic cost. So for example, in this Landau's bound problem, this is additional cost. This is actually very loose bound, but you see that when tau goes to 0, this additional cost also diverges. It means that if we perform an instantaneous resetting, actually infinite amount of thermodynamic cost is required. So in this sense, this instantaneous resetting is not the optimal protocol in the sense of thermodynamic cost. So we change the question in this way. So what is the minimum searching time for a given limited thermodynamic cost? So here we found the cost-time trade-off relation in the stochastic resetting process. So if you are interested in this matter, then you can listen to Dr. Priya's talk in the Friday morning session. Okay, so so these are my collaborators. The Professor Hyungyu Park officially retired, but now he got a new job new position as a distinguished professor in KIA, so we are working together still. And Professor Kwon and Professor Sang-hyun and Dr. Sang-hyun and Dr. Priyo and Dr. Jongmin, he is now in APCTP. Okay, so thank you for your attention.
So I'm just wondering, how are you defining dynamical activity for continuous systems?
Okay. Yeah, that's a good question. Yeah, as you mentioned that dynamical activity diverges in continuous systems. So here, in this system, actually, we make a coarse grain bit model. So even though this is a continuous model, so if the system is in this area, we say that it is in the one state, and if it is located in this area, then we say the memory is in the 0 state. In such a way, we coarse grain this model. So it is kind of a quasi-discrete model.
So it's an effectively two-state model, right?
Yes, right.
So is there any development to find the speed limit, for the continuous systems?
Yes, actually, as I mentioned that If we use some other statistical distance, so-called Wasserstein distance, then we can derive some speed limit kind of inequality. So by using Wasserstein distance, we can also make a speed limit for a continuous system.
Thank you.
So in your TUR derivation for this vision information, so you have taken a particular kind of perturbation, right, which is linear.
Yeah, particular perturbation, right.
So what if you take a different one? Will you get the similar kind of bound?
Yes, right. So we can make a infinitely many perturbation scheme. So then we will have infinitely different kind of inequality, right? So, but the thing is that among these infinitely many inequalities, what is physically meaningful? So that's the question. So this perturbation is, as far as I know, one of the most, it has a very meaningful result, so that's why people make a perturbation in this way.
Okay.
So for the overdamped system, in the TUR, all the quantities are sort of like physical observe. I mean, it's easy to interpret them physically. But in your underdamped, it was not clear physically what the quantities are. Like you have, the general relation that you derived for the underdamped system.
Yes.
Like physical interpretation of the quantities in the inequality is not very clear, right? Is that in the overdamped system, it was the average current and the fluctuation in the current.
Yes.
But in the underdamped, there's no such clear.
But as I showed in the previous example of a Brownian particle in a magnetic field, we can evaluate the work current, or we can also calculate the heat current, or in such a way we can observe some current, even in the
But the general form, can you show the general form that you derived?
Here. So what do you
Right. No, after this, I guess.
after this? Before that?
After.
So this is one observable here, work current in the underdamped Langevin dynamics.
Okay.
So this work done by non-conservative, or actually the same definition for overdamped system.
Okay. Okay, yeah, we'll discuss later.
If there are no other questions, let's thank the speaker.
thanks a lot for inviting me. It's I used to be in this institute, so it's actually homecoming for me. So thank you very much, Pinaki and Arnab. Yeah. So what I'll be talking about is given there is the and this is work done with a very talented postdoc Ayancha Rai Chaudhary and the student Saptarshi Dasgupta. And it appears in this recent archive paper. So my talk is going to be about active elastic systems, active elastic renewable systems, so constantly undergoing turnover and unbinding and binding back to the medium. And these systems exhibit tension force chains or stress fibers, as the biologists like to call it. And these occur as finite time singularities. So this is what my attempt will be in this talk. It also exhibits what we call fragile elasticity, okay? And it's these interesting sort of mechanical aspects that I'd like to talk to you about today. Yeah. So the system that I'm going to focus on is the interior of a typical cell. And the interior of cells such as these or suitable in vitro systems where the cell is now plated on a microfabricated substrate, for easy experiments to happen. These systems provide an opportunity to study rheology of this active renewable matter. And I think it should attract the attention of rheologists, I think. There's been a lot of work in this field, but the aspect of renewability has not been addressed so far. Mainly because renewable systems are it's difficult to make in vitro realizations of renewable systems. And these systems, as I said, exhibit these system spanning force chains. Okay, what is labeled here are actin filaments, actin fibers, and you see they form really bundled line-like structures, okay? And this is what I'm going to talk about. It's these system-spanning actomyosin force chains that I'm going to show emerges as a result of two aspects. One is active contractility coming from actomyosin, and the other is turnover of myosin in a strain-dependent manner. Okay, so these are the two aspects that I'm going to talk about. Further, you'll see that these lines, these singular lines, are sort of held at the boundaries, okay? And they are held at specific sites at the boundaries, they're called focal adhesion sites, and that's also going to be a crucial aspect of it, okay? So there's some internal, polymerized lines that emerge, and these lines propagate all across the scale of the cell, and at the boundaries, they are held together or they're anchored at special points. Okay, so this is the system that I'm going to look at. These actomyosin, as I said, they form cell spanning patterns like so, and indeed this is responsible for the overall shape of the cell, their size, and their deformability. Okay, so it's very crucial for the biology of these cells. Further, it's a lot of us imagine that this architecture actually controls internal organizations of organelles. Okay, and this is an aspect which is just being studied now. Oops. Okay. So the wide variety of mechanical responses that these cells show, it's a consequence of this active cytoskeleton that I'm looking at here. Okay, these green lines, as I said, they are the interior is formed by cell-spanning non-equilibrium self-assemblies of actin and myosin. Okay, filaments such as these. Now, what's crucial to realize is that these actomyosin filaments, they act both as force generators and force sensors. Okay, that is, they both exert forces and they sense forces, and the latter, namely sensing forces, is done by a strain-dependent unbinding. Okay, so that's what makes it very different from regular inactive materials. Okay? And it's this sort of contractility and remodeling that makes this system sort of an adaptive mechanical system. Okay? That is, it adapts to external forces that act on this. And in sort of changing its mechanical properties depending on what external forces are applied on this. The cell typically, and this is something I'll show, it typically explores the limits of mechanical stability. Okay, and that's what I'm going to talk about. Fragility is precisely that, about exploring the limits of mechanical instability. Okay, so now a little bit about the phenomenology. Okay, oh, I forgot. What I wanted to show you here is, of course, this is one aspect of what this marvelous actomyosin architecture in the cell does. Okay, giving rise to these force chains or singular lines that you see here. But the other one is coexisting with the singular structure. You find that it has these excitable waves that are generated. So you have a coexistence of these singular lines and excitability happening in the same system. Yeah? And what we'd like to show is how do local active forces drive this into a steady state which exhibits both this kind of architecture and excitability. Okay, so now a little bit about the phenomenology. There are 2 slides on a necessary phenomenology of actomyosin. So please bear with me. So the chains that we are talking about are built from actin filaments, these red lines, which have a certain polarity. They have a minus end and plus end because that depends on the local structural polarity of the filament. And there's a bunch of myosin motors, which was discussed in yesterday's talk. Myosin motors, which due to by ATP or hydrolysis or chemical fuel, it drives movement like so. For instance, this myosin head moves towards the plus end, and therefore the filament moves in this direction. Okay. Similarly here, when a bundle of myosins latch onto actin filaments like so, a pair of actin filaments like so, these heads move towards the plus end here, and this one moves to that plus end. Therefore, these filaments contract. Okay, they come together. Here you can see in this architecture, there will be an extensile strain. Okay, the filaments move away from each other. So typically, in a collection of actin filaments and these myosin, you get currents like this. You get states of contractility, where the filaments are compressed. You also get states of extension. Now, there's an interesting difference between these 2 things, and that is the following. That is, these filaments are easy to compress but not to extend. Okay, so they're anisotropic in their response, and that anisotropy is a consequence of this buckling, and it's precisely this nonlinear buckling that gives rise to an overall contractility in a random meshwork. So if we have a random meshwork of these filaments, this was shown by explicitly by Martha Lenz and Pierre Ranseraf, that a random collection of these actin filaments upon which you put myosin, bundles of myosin, will overall have a net contractile response. Okay? So that's so what you should take home from this is that actin filaments form a meshwork. They're held together by cross linkers, which gives this meshwork some elasticity. And on top you put myosin, and myosin, the net consequence of myosin is to apply contractile stresses. Okay? The contractility, as I said, is a consequence of this asymmetry between extension and compression. Okay, so this is the force generation aspect of actomyosin. The other was about force sensing, and so just a few words about that. Again, here now is the schematic of this actin mesh, a random meshwork. held together by cross-linkers, which gives it elasticity. Imagine you have a collection of different kinds of myosin, red and blue, which bind to this meshwork, and they bind with a rate Kb and they unbind with a rate Ku. Okay? It turns out that if you apply an external stress onto this, the rates Ku or the rate Ku can alter dramatically. Okay? So this is called catch bond behavior, and this is what this is the idea of force sensing. That is, some of these myosin filaments exhibit a catch bond behavior. If you look at this experimental curve of the bond lifetime versus the applied force, then that typically, in most cases, increases with increasing force and then typically saturates. Okay, so it holds. So when you apply a force, it catches on stronger. Okay, it's like a seat belt or something. Okay, which beyond a certain extreme force, it of course detaches. Yeah? So that's the aspect we'll be talking about, a catch bond aspect. Some molecules indeed show the slip bond, which is that you apply a force and then they give up very easily. Okay, so this is the two key words that people use to describe the stress-dependent release. One is called a catch bond behavior, typically exhibited by a lot of these motors, and slip bond behavior. Okay, so these are the two aspects that I wanted, phenomenological aspects that I wanted to describe: the force generation and the force sensing. Okay, so now let's try to address a sharp question. Okay, so what we want to ask is, how do local active forces that act on this actin and myosin, how do they drive dynamic long-range force patterning, as I showed you in that picture of the cell earlier? And indeed, how does it form, how does it give rise to the coexistence between these stress fibers and excitability? So there are two scenarios that one could address this question. Here is the schematic of a cell with this random meshwork of actin. And let's have a thought experiment where I don't have any myosin in the system now. Now I put myosin onto the system here. And what we want to see is whether myosin spontaneously segregates into myosin-rich regions and myosin-poor regions. Okay? So the myosin-rich regions have bundles of actin because they compress things locally, and the myosin-poor regions suffer from expansion. Okay? So this is the kind of question you want to ask. An equivalent question, and this is what we'll focus on, is to take two different kinds of myosin, myosin A and myosin B, both of which are motors. And what you want to start off with is a uniform distribution of myosin A and myosin B on this mesh, and you want to see whether they spontaneously segregate into a myosin A rich region and a myosin B rich region. Okay? So that's and both the driving force for these things is going to be local contractility and the differential contractility between myosin A and myosin B, and the differential turnover or unbinding from myosin A of myosin A and myosin B. Okay, we'll focus on this just to keep one story, but what I'm going to tell you is equally valid for this scenario. Okay. Yeah, so the background has cross-linkers, and therefore the background is an elastic substrate. Yeah, we'll assume that the cross-linkers don't unbind over and that's fairly valid assumption. So the background is an elastic system. Okay, so again, just coming to your point here, that so how do you describe how do you provide a hydrodynamic description for that system that I'm talking about? The background is an elastic system, so it can be described locally by a displacement field U, which is a function of both space and time. And from U, of course, you can define a linear strain, okay, epsilon ij, which is a strain, which are just how U varies over space and time, okay, constructed from derivatives of U. Epsilon there is just defined as the compression, okay, is a trace of this strain tensor, okay. So that's going to be the description of the actin mesh, okay, elastic actin mesh. The equations that mesh in the overdamped limit, the equations that this mesh is going to obey are that the local velocity of the mesh should be equal to the forces, and the forces are just the divergence of local stresses. The local stresses is a combination of the elastic meshwork, because there are cross-linkers which provide elasticity. There is an active stress coming from myosin, which binds and provides local contractile stresses, and there's some dissipative stress, which is proportional to the strain rate. Okay. Now, in this, the only thing, this is known, this is going to be linear elasticity theory. This is just viscous damping. Okay, so these two are well-known ingredients, but what is new here is this active stresses. New meaning it's been studied for the last 10 years, but it's okay. And these active stresses are going to be functions of the myosin density and the local actin density. Okay, and we'll have to, this is going to be the phenomenological input. We'll have to provide forms for how the sigma active depends on these two variables. Okay, so this is a simple force balance. Now, of course, there's myosin which binds and unbinds and binds and unbinds, so they have the dynamics of their own. The local dynamics of myosin is given by advection, is carried by the local velocity of the mesh, a diffusion term with the diffusion coefficient d, and then there is the binding unbinding. Okay, so this accounts for the local mass balance. The binding unbinding is typically, as we showed, has a catch bond behavior, therefore it is strain dependent. Yeah? So these two in these yellow squares are the phenomenological inputs we're going to place on this rather general elasticity theory. Okay, so as I said, the elastic stress is just linear elasticity. So sigma E, the linear stress, is the derivative of free energy with respect to strain, and it just has a bulk elastic, so that's a bulk modulus coupled to the compression, and the shear modulus coupled to the deviatoric strain. Okay, this is the coupling between the actin density and the local strain, which is a statement that the mesh density is slaved to the elasticity, okay, slaved to compression. By locally compressing the mesh, I'm increasing the density of the actin filaments. Okay, so that's that relation. So this is a rather well-known. So this is standard elasticity theory. Okay, for the ingredient that we need for to describe turnover is discussed here. So this is the rate of binding, which depends on the actin density, and the rate of unbinding. Okay, so. And we'll take the rate of unbinding to be a catch bond, and so strain dependent. And this is the form we take. This is the typical Hill form. Epsilon, remember, is the compression, so it's negative. Alpha being greater than 0 suggests as a catch bond. Alpha being less than 0 suggests as a slip bond. Okay, so you can see the consequences of this, of the state of the cytoskeleton as a consequence of both contractility, which I'll come to later, and the strain dependent unbinding. Okay, I'm missing a slide. Oh yeah. Okay. Yes. So it turns out that, okay, before I come to the form of the active stress, I'll just say that it's sort of it's suppose you have two different, so this was, this equation holds for both the species of myosin, myosin A and myosin B, and it turns out that it's easier to go to sum and difference variables. So that is the equation here. So again, force balance, that is the local velocity is equal to the forces, and this is the equation for the myosin A plus myosin B, the net density of myosin A and myosin B. And this is the equation for the difference variable. Okay, we're going to concentrate on this because I want to describe segregation. Okay, so this is going to be the crucial. It'll be the interplay of this equation with that provides all the magic in the results here. Okay, so now I've talked about the unbinding or the turnover of myosin. What I need to put is the other ingredient, namely the force generation. The force generation, as I said, is a function of the actin density and local actin myosin density, and it could just be taken as a more myosin, more contractile stresses, so to a curve which linearly increases and then saturates. Okay, so it's a very simple kind of form. So that's what I'm going to take here. It depends linearly on the densities of myosin, but it also depends on actin density. And actin density, remember, is slave to the local compression. So I can unpack this by sort of expanding about the uniform actin density and generate these strain-dependent terms. Okay, and these strain-dependent terms are a consequence of just expanding this quantity about the uniform mass density of the actin. The consequence of this is to renormalize the original stress-strain curve. Okay, the original stress-strain relation, remember, that we started off with linear elasticity theory, where the stress was proportional to the strain, okay, via this elastic moduli B and mu. Okay, but the inclusion of active stresses and the expansion of and the dependence of the active stress on actin density immediately renormalizes the form of the stress-strain relation. Okay. Yeah.
But this is hot materials, you don't have to take nonlinear elasticity.
Right. So that the nonlinear elasticity emerges from this. Yeah. Exactly.
But that is because of the active part.
That's because of the active part.
Without active, also it will be nonlinear. Right?
It could be. So right. So it turns out that the cytoskeleton, the actin mesh with crosslinkers behaves like an elastic system. Yeah. For very, very large stresses, because the crosslinkers start unbinding, and then of course something else happens. Okay. So the effect of this active stresses is to do three things. It provides an active pre-stress, okay, which depends on the local density of the bound myosin of ρ1 and ρ2. It renormalizes the elastic modulus B, and I'll give the form later, but it's again an activity-dependent renormalization of B. It becomes softer, as you can imagine. Okay, and it also provides a nonlinear elasticity theory, which stabilizes the potentially softening of this elastic modulus. Okay, in fact, what you can see here, for instance, is that the elastic modulus, which is the coefficient of the linear term there, gets renormalized by this quantity. Okay, this is the passive part, which depends on the concentration of crosslinkers. But because of activity, there's a softening of the elastic modulus. Regions with large values of phi, or right, if myosin 1 is more, or myosin A is more in certain region, those regions will have very small values of B, which can be driven to 0 and in fact negative. Okay, and that's where all the interesting thing is going to be. Okay, so activity, as I said, drives the elastic modulus to become softer, and in fact it becomes soft, and it has an interesting set of mechanical properties. For instance, this could be driven by making ρ and phi large. I can drive this to have 0 value. And 0 value is a different kind of elasticity. It's no longer elliptic elasticity. It's no longer standard elasticity of a material, but it gets driven to what's called a hyperbolic elasticity. Okay. You also find that, for instance, in the regime where, for instance, this is the effective B is 0, these systems are highly auxetic. Okay. That is, the Poisson ratio can be negative. Okay. So which means that if I compress in this direction, okay, so this is the conventional thing, is if I compress in this direction, it will expand in the perpendicular direction. But in these auxetic systems, if I, for instance, pull it apart in these directions, this one can go up. Okay? So, okay. This statement of hyperbolic elasticity has to do with the characteristics forming aligning as force chains. That means that in conventional elasticity, for instance, if I have a material here, and apply a point force, a point load at this point, then the stresses diffuse propagate diffusively in the material. However, in hyperbolic elasticity obtained when B here is close to 0, okay, the stresses propagate along rays, okay, and there's a very strict directionality associated with this, and this is what is associated with the emergence of force chains, as has been observed in granular media. Yeah, so.
Is it related to this anomalous elasticity?
What is anomalous elasticity?
So if you have an elastic medium,
Yeah.
recently there are some rocks
Yeah.
with the heterogeneity in the structure, then you put up at some local place and look at how stress propagates. Typically in the elastic media, you will see that this thing amplitude decays as 1 over r to the d or d minus 1. Okay, d minus 1, right? D minus 1. But then in anomalous elasticity, you will have a completely different behavior, and also in a length scale will emerge. That up to certain scale you have one behavior.
I see.
And then at a later scale you have 1 over r to the d minus 1 behavior.
I see.
But maybe these systems are probably also susceptible to that.
Could be, but so these are overdamped systems, right? I mean, in the case that you're talking about, are they overdamped systems? They are.
So,
Okay.
yeah,
Okay.
it's
Okay.
a dense.
Oh, I see. Okay. Yeah, we can discuss that. Oops, what happened here? Oops. Sorry, something happened here. Huh? You shouldn't have asked that question.
Do you have other textbooks?
Yeah. Huh? It's here, but it's not there.
You have to slide it. No, it is there in that.
No, it's here, but
Yeah, go to the other desktop. Yeah. The 3 fingers swipe.
no. You're opening my secrets.
Not revealing too much.
Maybe we can start again. Where is the? Here. Should I start again? Huh? Maybe I can just go here, no? Yeah. Okay. Okay. Yeah. So I hope you got the thing that because of a combination of contractility and binding, you get this very interesting mechanical behavior of softening of the elastic modeling, leading to even being driven to hyperbolic and parabolic elasticity. So that's what I wanted to say here. Okay, the other aspect that is interesting arises by doing a linear stability analysis of those dynamical equations that I talked to you about. The dynamical equations which was about strain and the density of bound myosin and bound myosin. Okay, so what we find is that, for instance, just look at this. This is the phase diagram in the passive elastic modulus, so the bare elastic modulus on the x-axis versus the contractility, average contractility in the y-axis. And you can see that for very large elastic modulus, if the original the original actin mesh is very rigid, a lot of cross-linkers, then that system is going to be very stable to the binding and unbinding of myosin. And if it is very weak, however, the local binding of myosin is going to apply huge contractile stresses, and that gives rise to sort of contractile instability. The whole thing just collapses. Okay? In between, in between these two extremes is an interesting region where the two myosin species segregate from each other. Okay? And so what happens is I start with the uniform distribution of myosin A, myosin B. Over time, there is a spontaneous segregation of these two stresslets or density fields corresponding to myosin A and myosin B. This is the dispersion curve of that, which shows you that it's unstable to the formation of segregated domains. But this should come as a surprise because there was no interaction between the two species of myosins. Okay? The segregation is not as a consequence of some gradient of chemical potential, which is the usual segregation of two components, but this is coming because of its interaction with the underlying mesh. And so the driving force of that turns out to be the elastic stresses stored in the meshwork, and you can show that to linear order, this acts as a Lyapunov function. That is that this quantity W dot, namely this is the elastic power, that is a decreasing function of time. Okay, and so it's this elasticity of the underlying mesh which connects the two different species of myosin that gives rise to the segregation. Okay. A sort of interesting feature is that the segregated phase has, this interesting, so this is showing the segregation, right? I start off with where you have a homogeneous uniform distribution of myosin A, myosin B. The segregation in this regime, the segregation instability develops, and you start picking up a non-zero wave vector which grows exponentially fast. Okay? But if you look at the segregated strips of myosin A, myosin B, then they have this peculiar form. Look at the density of myosin A, let's say, within that segregated region. It shows a peak in that, but myosin 2 also shows a peak. Okay? And this is because of, which is different from oil and water. Okay? So it's an interesting observation here. And this is because that both myosin A and myosin B have catch bonds. Okay? And that's the moment you have one catch bond, one slip bond, the peak of myosin A will be separated from the peak of myosin B. No. This is happening again. Okay? Okay, but now what happens when you have so far it is all about linear regime, okay? The linear segregation following the initial homogeneous configuration. Okay, so you now find it, so now as time progresses, of course, nonlinearities kick in, and you can ask how does the pattern of myosin A and myosin B evolve over time when you include the nonlinear terms in the equations of motion. Okay. So in conventional phase segregation, let's say oil and water, this is the scenario. You start off with a homogeneous mixture of, let's say, oil and water, or two different components. It quickly undergoes a segregation at low enough temperatures. You have the pink region segregated from the blue. And nonlinearities then go to create large macroscopic domains, okay, such as shown here. So the domains just increase in time and typically go as some t to the 1/3. Okay. What happens here? What happens here is the following, and this is quite peculiar and is a consequence of the activity in the system. What happens here is that the initial linear segregated domains, as shown here, okay, very quickly shrink to these singular lines. Okay, and that's because there are two aspects of the physics that is different from the usual part. One is that there was the sigma. There's an active pre-stress. Okay, so rho 1 is the more contractile element compared to rho 2. Contractility then makes this domain shrink. So if you start with a domain like this, contractility then makes the domain shrink. Okay, because of the contractile forces, and so these growing patches then very quickly in a finite time reduce to these singular lines, okay, because of contractility. So it initially linearly segregates, but then contractility pulls it back in. Okay, and it does so in an interesting way. It does so by the appearance of these finite time singularities. That is, that is, as soon as it grows to a certain extent and accumulates enough of the contractile species, it starts the contractile stresses due to this enhancement of the myosin A shrink the growing domain, and it shrinks and it has it shrinks and it has a certain scaling form where the density of myosin A, for instance, has this kind of scaling behavior. Okay, the width of the domains shrinks as t minus t0 to the power of 1/3, where t0 is this finite time singularity. So I hope you get the picture. Initially, a homogeneous phase segregates. The segregated domains accumulate more and more of the contractile species. The contractile species then brings the domain back to thin lines, okay? Thin singular lines. And the thin singular lines have a certain scaling form which one can derive from finite time analysis. Wow. So, I don't know what to do. What has happened?
You were still seeing your.
I can see it here, yeah. And this time you didn't ask a question. So. Now it, yeah. But where's the mouse? Okay. Yeah. Oops.
This side comes.
Yeah. Yeah.
Here.
Yeah. Yeah. Okay. How much time do I have now? A lot of time. A lot of time. Okay. Okay. So, this analysis, I must say, was done. The scaling form was obtained by solving the one-dimensional form of these equations using matched asymptotics and dominant balance techniques to give rise to these scaling variables. In 2 dimensions, it turns out that it's slightly more complicated. One needs to include anisotropic stresses, which arise because actin actually is a filament, okay? And so these contracted regions of actin, as shown here, for instance. Okay, the contracted regions of actin are actually filaments. Okay, so when you get to this configuration, you have to include anisotropic anisotropic contributions to the stress, and if you do so, you get the same kind of physics. So it turns out that what you find is that if you start with a homogeneous distribution of myosin A or myosin 1 and myosin 2 embedded in a random meshwork, then you quickly start getting these lines, singular lines in 2D. In 3D, they form singular lines and planes, and so on and so forth. Okay. So in the extreme limit, once they form these singular structures, then you can ask, what is the mechanical, what is the mechanics, or what is the force balance, mass balance, and torque balance for these singular lines? And what you find is that you can derive active versions of the Young-Laplace equation, which I won't tell you about here. But it's an interesting thing. For instance, if you take this just says that the elastic pressure difference between, so this is the singular line I'm talking about. PE here is the elastic pressure difference between this region and that region. PA is the active pressure difference between that region and this region, and this sum of the things, so the tension multiplied by the curvature plus these jumps in pressure across the line, is proportional to the normal component of the velocity of the line. So for static lines, okay, you can see that this would be the active version of the Young-Laplace equation. Okay, and yeah, so there are interesting consequences of that. You can also take these lines and study the dynamics of lines and look at the merger between 2 lines, whether the lines go through each other. okay, and so on and so forth. And there's a whole rich dynamics which we are currently studying. But here is an experiment which shows the dynamics of these lines. Okay, these are cells which are again embedded in microfabricated environments, and these lines here are actin lines which are bundled because of myosin. And if you look carefully, you can see that you can see this one line here which has emerged from that bundle and then moves. There are lines which coalesce, and so on and so forth. Okay, so this is a beautiful recent experimental work by Vigneault et al. In this, and this is an early simulation by François Nedelec's group, which shows these lines. Okay, you see, it's now looping, but you see the formation of these singular lines. Sorry? Oh, well. Okay. Yeah. So now you could, in a cell, of course, there's a finite boundary. 5 minutes? Yeah. In a cell, you have a finite boundary. And so the question now is, when you have these bunch of lines in the interior of the cell, how do they interact with these boundaries? In fact, these boundaries are called focal adhesions, and they anchor these lines. Remember, this is what I was telling you in the first slide. Okay. So including these anchors at specific points, you can stabilize these moving lines, and they form this web-like structure. And here is what I meant by fragility. The whole network of these lines, which are stabilized because of the anchoring at these precise points, changes when you displace these anchoring points by a slight amount. Okay? So even the slightest displacement of these anchoring points will remodel this actin meshwork. Okay, and this is what is called fragile matter. Recall that this fragility is different from the fragility in granular media. That in granular systems, the fragility is due to the compression between grains. Here, the fragility is because of the tension between the lines. Okay, so that. Okay, here are some experiments which I won't go through, but they are reflective of the kinds of analysis that we have done. And maybe I'll skip this in the interest of time. Or do I have the time? Okay, oops. Okay, I have 4 minutes. Okay, so far I've been talking about these emergence of these singular lines, which are anchored at the boundaries by special anchoring molecules such as focal adhesions. And remember, in the first or the second slide, I told you about the coexistence of these lines with excitability. Yeah, and this is what I'd like to demonstrate here. Again, so what I've written down here is taking the dynamical equations, namely the equations for the strain and the density of bound myosin, and then linearizing it and writing this down as a time derivative of the Fourier components of the strain and the two density fields with a dynamical matrix. Okay, so this is just the linearized Fourier transformed version of the dynamical equations. The reason one does this is that this here is the dynamical matrix, and once you look at this, it turns out that the active contributions to this dynamical matrix make this matrix non-Hermitian. Okay, and it's the non-hermiticity of this that gives rise to this interesting excitable phenomena. As you move in parameters, so a consequence of the non-hermiticity of the dynamical matrix is the fact that the eigenvectors, which tell you how perturbations propagate, the eigenvectors need not be orthogonal. Okay, and in fact, as you change parameters, the eigenvectors can coalesce. Okay, 2 of them can coalesce, or 3 of them can coalesce to give rise to what's called exceptional points. Okay, and the exceptional points are an interesting thing. If you look at the phase portrait, a typical phase portrait about these exceptional points to remind you are regions in parameter space where the eigenvectors coalesce. Okay, if you look at the phase portrait, then this is the one. The linear stability analysis tells you that there should have been a putative fixed point here. Okay. However, the phase portrait gives you flows like so. Okay. So if I start with an initial condition here in this variable v and u, then the flow lines will take you all the way, very far and then come back. And if you start from close by any point here, okay, you're driven all the way for very far, then you pick up nonlinearities, and then the nonlinearities can drive you to another unstable surface. Okay, so this is what happens typically in the vicinity of these exceptional points. You find, and this is well known in fluid mechanics, for instance, and it's known that linear analysis sort of does not work in the vicinity of these exceptional points. But what's interesting for active matter systems is that the exceptional points are sort of gateways to traveling waves. Okay, and what we find here, for instance, you get these traveling in between the contractile instability and the oscillatory phase. You start getting traveling waves as shown here, and I'll play a movie if I can. Oops, can't see the cursor. Okay. Okay. Anyway, I can't seem to find the cursor, but this would have shown you traveling waves. Okay, and then you get another phase in the vicinity, in the boundary between the oscillating and the contractile instability. You get another phase called a swap phase, which is a standing wave. Okay, where you have large concentrations of myosin A, myosin 1, okay, and low concentrations of myosin 1 there, and it sort of swaps like that. Okay, it's a standing wave that you get. Yeah, so this happens in coexistence with the stress fibers that I talked to you about. Okay. Okay, I can't see the. Okay, so I'm going to end the talk with the final few remarks. So what now the cytoskeleton is built up of more than actin myosin. It's also built up of microtubules, which are very large compressive filaments within the cell. Okay, and so one could ask, what is the how would you now describe the mechanical properties of a cell interior, which is comprised both of actin, myosin, and microtubules? Okay, and this is something we just started looking, and the reason why this is interesting is the following. There has been a recent proposal by Ingber that the interior of the cell behaves like what's called a tensegrity structure, yeah, where the microtubules are rods, okay, and they hold all compressive load, and the actin held with myosin forms tension, okay, forms rubber bands, okay, and this tensegrity structure was an old proposal and a challenge by Buckminster Fuller, who challenged the architecture and the engineering community to build structures such as these, which are held by tension, by the strings, okay, and they have compressive elements which are isolated. Okay, this is, so for instance, here is a structure where you can deform it, and the thing will bounce back. Okay, these are amazing structures. I just saw the structure out there in the building, and this is a tensegrity structure. Okay, once you go out, you'll see that structure here. It's again held by these strings, and the moment you cut these strings, the whole thing collapses. Okay, so this is very different from buildings such as these, which are stabilized by compression, these are stabilized because of tension. Okay, and there's been an interesting proposal that the cell, the way to understand the mechanical behavior of the cell is to think of it as a tensegrity structure. Okay, now what we have been trying to do is, via this formalism, we would like to arrive at a dynamical theory of tensegrity, writing down dynamical equations for myosin, actin, and microtubules, and hopefully this will give us a dynamical theory by which we can understand tensegrity-like structures. Okay, so what I've talked so far is about the patterning of forces forming singular lines arising from the action of force generation and force sensing by myosin on actin. Okay, so these form the singular force chains that I talked about. So this is the stress fibers, and these stress fibers are stabilized in a finite cell, is stabilized by boundary elements called focal adhesions. This ensuing structure exhibits fragile elasticity, and this may coexist with excitability such as turning waves, such as traveling waves and swap phases. Okay? And as I said, what we'd love to do now is to try to formalism for a dynamical theory of tensegrity. So the work on this, oops, again, that was the most important slide, and those again vanished. Okay. So now I can see it here, but not here. Huh? It's some full screen. It says no available indoors. No, I can't do anything.
Oh, it is frozen.
Ah.
No, this is frozen completely. No, it is.
No, no.
But here it is frozen.
Yeah, here it is. In any case, that was the last slide. So this entire work was done by this very talented postdoc, Ayan, whose face I can't show you now. Oh yeah. Oops.
It really goes CVT. Okay.
Okay. I'll just show this. This way I don't need to show it. Yeah. Okay. By Ayan and Saptarshi, who was a student there, and there's some previous work in collaboration with my experimental colleagues, Thomas Lequi, which discussed the emergence of traveling waves in tissues, okay, using a similar kind of formalism. So thank you for your attention, and if you have any questions, I'll go. Any questions? Yeah.
So it's the last thing that you said about tensegrity.
Yeah.
So because you need this very fragile balance between compression and tension,
Right.
Is this how it gets to quickly remodel and become, is that what you're trying?
Yes, exactly.
And then how does it not get buffeted by fluctuations and just get washed out? Meaning, how does it maintain despite whatever else is?
How is it robust? Yeah. So this is where I think these focal adhesions play a role. So if you take a cell and detach it from a substrate, then you lose all these focal adhesions, and then the actin meshwork totally collapses. Okay, so there are these pivots that are there. Yeah.
This normal gelation also has a finite time similarity because they are also from these.
Yeah, I presume. Yeah. You're right. Yeah. I mean, this thing is very similar to gravitational collapse and finite time.
Gelation.
Yeah. There also they talk about gravitational collapse.
These streaks and these cosmic.
Right. Exactly. Yeah.
So in the context of the mechanical metamaterials,
Yeah.
What would be the Poisson ratio of such kind of structures? Would it be by any chance
Yeah. So
negative?
right. So there's been a lot of work recently on constructing these mechanical materials with auxetic properties. So the Poisson ratio is negative for those things. But here it can be really very negative.
Very negative.
Yeah.
Because, for example, even origami structures.
Yes, absolutely.
Can
Yeah, exactly. Yeah.
Thanks. Yeah.
Other questions?
You know, one of the things that happens here is that this system can dynamically explore many different kinds of marginal elastic states. So it can become what's called an ether state, you know, where B plus mu, that the compression modulus plus the shear modulus is equal to 0. Okay, and it can become a fluid, what's called a fluid elastic state, where the shear modulus is 0. with compression. It's still an elastic system, but the shear modulus is 0. So these are called marginal elastic states. And this system of active myosin can explore all these different configurations.
I have a question. So you mentioned about the passive nonlinearity, about you haven't considered unbinding,
Yeah.
but I guess unbinding will give you only the softening kind of thing, but this passively these systems also show strength stiffening.
Yes.
So that kind of nonlinearity do you need to consider?
So in this case, we've assumed that the background passive system is a simple system.
Linear elasticity.
Linear elasticity, and all these interesting effects are happening as a consequence of activity. But you could make it more complicated, as you say. You could make the background itself have strain stiffening coming from unbinding of cross-linkers.
Okay.
That's how it typically happens. You have
You can have stretching of cross-linkers also, like flexible
yes,
ones.
exactly. So this is, people have studied a lot on this a lot, yeah. So you can make your background theory more and more complicated. Yeah.
Okay,
Yeah.
thanks. Okay, so if there are no more questions, let's thank the speaker once again. So we'll meet here at 4:30 for the next session. Pinaki? Okay, welcome back to the last session before the post-test session for the day. Our first speaker, we have three speakers. First is Suman Datta. So he'll be telling us about liquid state properties and jamming dynamics of persistent athermal active matter.
Am I audible? Hello everyone, I am Suman, I am from ICTS, and this is an work going on in collaboration with Pinaki Chaudhary from IMSC, Madan Rao from NCBS, and Chandan Das Gupta from ICTS and IISc. So this is still some of the results that we have obtained very recently. So the kind of results that we have obtained are some of the unusual features of the liquid state properties in active matter systems, which are very dense, and also that show jamming. So I'll try to summarize some of the results that I have obtained. And so the theme for today will be very nicely illustrated in one of the pictures that I got from Quanta magazine. So the theme would be this is going to be the broader theme for today's talk. So you can see that there is an emergence of the structure from disorder. So we'll start with the persistent athermal active matter, which was introduced in the beginning in the morning session by Rajesh. So, and also I'll talk about different the kind of models, molecular models that show cell jamming, and we'll touch upon the complexity of active matter, and that is clubbed with the physics of glass here. So it's a very difficult problem that we are trying, and again, to emphasize the focus will be the order in this disordered landscape. And also again, to refocus, the focus would be on the jamming dynamics of this kind of system. So to start things with active matter, so this has been quite discussed today and also from yesterday. So these are the bird flocks. Some of the examples are the bird flocks, also the school of fishes, and this picture also Shamriddhi discussed in the morning. So these are the self-propelled objects that actually converts energy into motion. And out of this active matter genre, we'll focus on a particular set of active matter which are athermal in nature, so that are not responsive to the thermal fluctuations and which are very dense. And also they are persistent, means the orientational degrees of freedom are quenched. So some of the examples are the cells and the tissues, which also show some sort of glassiness. So the thing becomes are the athermal persistent active glassy matter. And the kind of glassiness that I want to refer is the property of jamming. So jamming is basically how things approach to a rigid and mechanically stable state. And this is a movie on cell jamming. So these are the cells. The cells obtained from the epithelial, so these are epithelial cells from, so this is called HBEC or the human bronchial epithelial cells that initially are in the liquid state, and then you can see that their motion cheeses, and at the end they are they get jammed. So a representative cartoon is this. So this is a jam state where you can see the cells do not the cells are not in the mobile state, but they only vibrate around their mean positions. And this is what an unjammed state where things are mobile. So the kind of transition we are going to refer are initially those are at this unjammed state, and how do they approach to the jam state. So this is our problem. And Recently, not very recently, in 2019, the similar kind of jamming dynamics was looked by Peter and their colleagues, but not in the active system, but they looked into the passive jamming and its root. So they start with some liquid-like state and how it reaches to a jam state. This was the jamming dynamics in the absence of the active forces. Now, the question that we try to understand, can these jamming states could be achieved in presence of activity or not? Shayantan also referred to another kind of jamming in presence of the shear. So that was the shear jam states. So these are the passively jammed state, and the another class of jam state I am going to refer are called the actively jammed state. Question is whether they have any distinct features or not. So one particular result that they obtained was this power law decay, and we will try to address whether we will get similar kind of behavior or not. So this is with increasing packing fraction, and also the root comes through some heterogeneity. So these are the displacement maps, and you can see these swirls that has got some symmetry, which is very much like the SLB events. So we'll try to look at the similar kind of dynamics in presence of activity. So our goal would be two things. First, we need to characterize the liquid state that we will start with, and then we'll look into the dynamics as things get jammed. And some of the results earlier our group obtained, they obtained this kind of phase diagram, and jamming was achieved in this infinite tau p limit. So we'll focus on this limit, so where the persistence time is infinite, and we'll vary the f. So the system is a bidispersed system, so we have two different types of molecules, or you can see particles, which and every particle has got some self-propulsion forces, which is f. So that's one parameter for us. The jamming could be achieved by many other parameters, but for our problem, this is the only parameter for us. This is the interaction between two particles, and we have the friction. So again, I'm emphasizing one feature of this system is that the force directions do not change with time. So we don't have another equation of motion for theta. So we'll start. So another result from our earlier work from earlier work. So what happens actually, this system actually shows fluidization beyond a force threshold. So, and this is how the kinetic energy increases with the active forces. So for certain values of the active force beyond a force threshold, so there is non-zero kinetic energy in the system, and this is one typical state which I am showing. So this is at f equals to 3. So here you can see these particles are color coded with the velocities, and lighter color are the particles has got higher mobilities. And what happens for this high active forces, the system with high active forces, if you quench the active force, then actually what happens, it shows jamming. And so initially, so you can see this state, and then with time, you can see that some activity you can see. These are the kinetic bursts, which is very similar to the plastic events, and so there are multiple bursts. This is the same system is shown in terms of the velocities and the active forces, and the end state is a jam state, which is a mechanically stable state. So it's a completely force balanced state. So we'll try to address what happens to the length scales at this. Is it possible to extract some kind of length scale in this state, and the time scales associated with the jamming, and is it possible to connect these two things? I have only 5 minutes. Okay, fine. Okay, so this is the route to jamming, and you can see that this is the initial state. What happens for f equals to 0, this goes down and it reaches to the jam state. And in presence of the activity and with increasing f, So the dynamics changes, and there is some sort of plateau before it goes to the jam state. And for very high F, so it doesn't reach to the jam state within this observation timescales. So and this is the different cases. So initially you can see this the same state. These are the jamming dynamics for different values of F. So F is equal to 0 represents this one, F is equal to 1 represents this one, and F is equal to 1.65 represents this one. So this one is short-lived, and this one you can see that it's searching, keep on searching for minima, and it takes longer time to reach the minima. So the system to system and run to run things change. So there exists some sort of stochasticity in the time of time to jam. So for each of the values of the F, so there exists a probability distribution of the time scale which shows like that. And if one extract the mean jamming time scale, so this is the associated time to reach the jam state. So it grows this way with the active force magnitude. So initially there is a divergence, and then beyond the force threshold, so there exists an exponential rise. So which is very similar to this recent results from Shrikant Shastri's group. So this is very much like a fragile to strong loss transition. And one question might be whether this has got any analogy or resemblance to this one or not. So this is, and also this dynamics has got a very strong system size dependence. This is for F equals to 0 for different system sizes. So all of them goes to the jam state. But however, the initial state is not identical for different system sizes. This is also this is very much same for F equals to 1. And also we can see the similar kind of behavior in presence of the active forces. So the time scale associated for all the cases, if we now try to correlate all the time scales with the system sizes, this is the picture. This is in the log-log plot. So this is how the time scale grows with the system sizes. This is in absence of the active forces. This is in presence of the active forces. So both as power laws, only the slope changes. So what happens to the initial state so we saw the difference in the initial state, and this is what happens to the distribution of the initial states. So these are the kinetic energy distributions for different system sizes, which shows a shift with the increasing system size. And this is the potential energy, and this also shifts to the higher values with increasing system sizes. And this is the velocity correlation for the set for all the system sizes, which shows an increasing order with the system size. Now what order it represents to? So you can see these swirls for different system sizes. So these are this is a plot for n is equal to 4,000, and this is from n is equal to 10,000. You can see these swirls have grown. So this increasing correlation are representative might represent the structure of these velocities. This has also been reported from work from Ludovic's group, and we try to connect the increase in the correlation length with the system sizes, and that grows in the power law fashion. So the xi goes as root n. So means this is things have become critical, and the correlation is growing with the length. This is increasing with the L, and this is the time scale and the length scale. We're trying to correlate the time scale and the length scale. So again, both are power laws, and only the exponents change. So the initial state, that is actually determining the dynamics of jamming. This is one result, and this is some sort of movie of the partial velocities, the x component and y component of the velocities. So this is the kinetic energy time series, and this is the velocities, and this is the total velocity, and you can see those events, and you can see this intermittencies prior to the jamming. So So these are our main results, and again this is a fluidization dynamics, and this is a jamming dynamics. So you can see these velocities and the correlated velocities, which actually in the process of jamming again shows some sort of activities before it goes to this mechanically stable state. And summary, we can summarize the results. So activity driven dense liquid jams by lowering active force magnitude. The jam state is a force balance state. The relaxation process is heterogeneous nearby the active force threshold. We also saw the 3-stage relaxation, the initial short time decay, and then we saw a plateau that has got, there was a plateau that is representative of searching for minima, and then we had the relaxation within the minimum. And the whole dynamics is governed by the initial state and its properties. So with this, I'm going to stop.
Okay, thanks. We have time for a couple of questions.
Which one?
You had those bursts of activity coming out. I don't know if it was the one before this. This one. When you, if you see the video. So I was curious, is the dynamics facilitated in this? Maybe I've asked you this before, I don't know. Okay, maybe then I'm coming back to the same.
No. So we are trying to understand these events and how does, means the local, the spatial relaxation of the local quantities like the stresses and those things we are trying to understand. And, again, this is a very difficult problem. We need to understand, we need some time to understand. Any other advice, sessions? Yes.
So for your velocity correlations, how does the length scale with n? Is it just linear system size, or is it something more complicated?
So this xi goes as root n. So it means with this is going with L. This is in 2D.
Right. Okay. And is there a dynamic exponent between length and time, and what is the ratio of the exponents?
This one?
So you have an exponent for length and for time, so I was curious what the dynamic exponent is, so the ratio of the two.
Ratio of the
length and the time scale exponent.
Okay. So these are, so the exponents we have figured out. So this is tau j and this is log of xi. So the exponents for in presence of the active force, in the absence of active forces, the slope is close to 1. Okay. And in presence of the active force, this is 5. This is for f equals to 1. Now it will be dependent upon the values of f.
Okay.
Because as you are going away from the threshold or close to the threshold, it will determine the time scale to jam.
Okay, thanks.
Okay, if there are no other questions, let's thank the speaker once again. Okay, our next speaker is our Sarvanan. So he'll be telling us about surpriser analysis of Fokker-Planck evolution in the phase space.
So good evening. First, I thank the organizers for giving the opportunity to present the talk. My talk is about surprisal analysis of dissipative evolution. Here I will introduce the maximum entropy approach to understand Fokker-Planck evolution. So I'll start the introduction of surprisal analysis by revisiting the principle of maximum entropy. In statistical mechanics, the distribution over the phase space can be inferred based on the observed expectation values. The inference is non-unique. The unique inference can be made by maximizing the entropy. So in the resulting maximal entropy form, the observable constraints appear in the exponent of the distribution, and the lambda j's are the multipliers that imposes that these constraints are satisfied. So this approach can be generalized to evolving systems where the evolving distribution maximizes entropy at every instant. So now all the time dependence is taken up by the Lagrange multipliers, and now we recast this interpretation in terms of surprisal. Surprisal is a log probability measure. Now we can see that the constraints of the evolution appears as a linear expansion weighted by the Lagrange multipliers. So when a set of constraints reproduce the exact distribution, then we call that the set of constraints form a closed algebra. So for reversible evolutions, the approach starting from the maximum entropy in reproducing the exact dynamics is already been established. Now I extend this analysis to the irreversible case. So I start with the simplest possible description of an irreversible system given by the Fokker-Planck equation. The Fokker-Planck equation models a system embedded in a dissipative environment. The first two terms are the forces from the environment. The other two terms are the Newtonian evolution. Now, motivated by maximal entropy, I can rewrite the dynamics in terms of surprisal that characterizes deviation from a prior distribution. So the prior distribution is the stationary solution of this equation, which is the Boltzmann distribution. So in a while I'll explain why do we shift the reference to a prior distribution. So the algebra of constraints that reproduce the dynamics can be determined from the equations of motion. For example, if I insert this expansion into the first equation, then we can see that it leads to a closed set of equations for the multipliers, and further that this set of constraints can also reproduce the exact distribution. So the first term of the expansion is the normalization constraint, and we have the expansion up to second order moments. The last term is the cross correlation, which signifies the energy transfer between energy conversion between kinetic and potential energy forms. So this way the total evolution can be replaced by the evolution of individual constraints. Since the surprisal is defined as a deviation from stationary state, the Lagrange multipliers quantify the disequilibrium present along every constraints at all times. So here I discuss the relaxation in the mean value constraint by plotting the Lagrange multipliers as a function of time. We have two known scenarios. One is the slow relaxation in the momentum, and other is the overdamped relaxation. So the longest time constant in these two kinds of relaxation determines the limiting dynamics. So this way the total evolution can be studied using individual contribution of constraints at all times. Now I proceed to the bistable case where we have two potential wells. So a low energy population which is stuck in either of a potential well can climb the barrier when it is when there is a environmental fluctuation. So for this problem, the expansion of constraints, so they do not form a closure. For it is due to the quartic term. For example, when I solve for second order moment in P, I require fourth order moment, and it further requires sixth order moment, and there is this iteration diverges indefinitely. So therefore, we cannot have a expansion of surprisal that is finite for this general case. But yet in a high barrier limit, the high barrier limit is of is a physical limit of interest to Kramer's problem in relation to chemical kinetics inside solutions. So if the wells are very deep, then there are no to an excellent approximation there is no net transition. So using that we can write maximal entropy form separately for the two wells. So here I take one correlated Gaussian for the first left well and the correlated Gaussian for the second well. So using this ansatz, we can study the evolution of the distribution using the evolution of constraints. So here I show the evolution inside the left well. So we can see that there is a time scale separation between a local equilibration of the distribution, that the distribution attains a steady value when the net flux between the wells is not yet equilibrated. So this condition is called quasi-stationarity, which is a feature of when the barrier is very, very high in comparison to a typical fluctuation. So in the long time, the net flux equilibrates and the branching between the wells achieve a steady value. So regarding this value, we provide the maximum entropy interpretation for the branching between the wells. So to do it, we group the total members of the distribution into those belonging to the left well and the right wells. Now I can write the expression for the entropy using the composition of these two subsystems. So maximizing entropy with the subject to known constraints can results that the branching ratio is just the ratio of partition functions. So for our case, when the mean energy is constrained, the branching ratio becomes as this. So in the deep well limit, when the left and the right well are just shifted by a constant given by the shift in their ground state energies. So in the high barrier limit, the population branching just becomes the Boltzmann factor, where EL and ER are the ground state energies of the wells. So what I presented is that we presented maximum entropy motivated approach to a simplest possible dissipative system. So the Lagrange multipliers, it quantified the disequilibrium along each constraints to the total disequilibrium at all times. So thus offering a detailed view of the dynamics. Knowing the constraints replaces the need to handle the large data for the distribution. So this is also useful in compaction of large data. Any evolving system can be studied in detail by identifying the set of constraints. So here I showed that 6 constraints are enough to reproduce the dynamics of a parabolic potential. Using surprisal analysis, I highlighted the dynamics of dynamics in a double well potential. So I would like to thank my supervisor, Professor Raphael David Levine, and all my friends for their valuable time and discussions. And I would like to thank once again to the organizing committee and you all for your attention.
Yeah, we have time for a few questions.
I see the last slide.
Yes.
So in the last slide, I did not know the slide before. Yeah, so this last formula, right, this continuous case, the ratio between this, I mean, this we know, right, a priori.
Yeah,
So
this is
what is it? So I did not really follow like this part, like what you were trying to derive. I mean, what was the point here? So, sorry, Jay, you just went very fast, so I missed the point.
So we have these two wells, and we have the eventual branching between these two wells. So we know that it is the ratio of partition functions. It's just the that it can be reduced to this Boltzmann factor when the wells are very deep, and it's an interpretation using maximum entropy. That we know that the branching is given by ratio of partition functions. Yes.
Other questions? Okay, if not, let's. Okay. So the last speaker of this session is Ofek L. Bonomo. He will be telling us about loss of percolation transition in the presence of simple tracer media interactions.
Okay, good afternoon, everyone.
So I remind
you. Yeah, sure. Okay, so good afternoon, everyone. My name is Ofek Lauber. I'm a PhD student in the group of Professor Shlomi Reuveni from the School of Chemistry in Tel Aviv University. And today I'm going to talk about my recent work, which is title is given in here. But before we start, let me just thank the organizers for this amazing opportunity. And on a more personal level, I want to thank Dr. Arnapal, who was a postdoc in the same group in which I'm doing my PhD today. And from the first day, I think he was not only a group member for me, he was a mentor, and he was a good friend, so I want to thank him for that. And I also want to thank him and his students, VK and Arup, for the amazing hospitality here in Chennai. So now we can start. So let me just give you an outline, a brief outline of this talk, so just to get everyone up to speed on what we are going to discuss today. So today I'm going to introduce the Sokoban random walk. What is the Sokoban random walk? This is just a model for random walk in disordered media with tracer media interactions. I'm going to use this model that I've developed with my PhD advisor to show you how this interaction, the introduction of these interactions, is going to lead to a significant deviation from a simple random walk model in random environment, which is the anti-Laberneff. And then I will dedicate the rest of my talk to show you how to use or utilize a scaling approach to estimate the MSD of such random walker. So let's start, and I will start with explaining what random walks in disordered media are. So consider the following two-dimensional arena. So this is the arena, and we have a simple random walker starting at the center of this arena. What do I mean by a simple random walker? This is just a random walker with equal probabilities of going up, down, left, and right. But now there is a catch. Here you can see that we have these black tiles, and these are just tiles which are occupied by some obstacles. And we scatter this obstacle with some fraction rho. So in order to understand the dynamics of a random walk on such an arena, let's take a look at the two extremes of this model. So on one extreme, we have density which is 0, meaning that all the sites on this arena are accessible to our random walker, and in this case, we have free diffusion. This is pretty simple. On the other extreme, we have density which is equals 1, meaning we cover with obstacles the whole arena, and now there is no room for the random walker to move, and in this case we have a constricted random walk. The question now is what happens in the gray area between these two extremes. So luckily for me, luckily for us, 50 years ago, Pierre-Gilles Lejeune, who is a Nobel Prize laureate in physics, he posed this question and also gave an answer to it. And he did it using the Antin-Labernev model. So what is this model? Well, we have a Labernev, of course, which is just a two-dimensional arena covered with obstacles with some initial density rho, and we have this ant, which is basically just a simple random walker starting at the origin of this arena. And now we ask ourselves, how can we calculate the MSD of such a random walker? So let's, in the light of the previous slide, let's take a look at the two extremes. So one extreme is the extreme of low density, and in this case we know that we have free diffusion, right? So if we look on the left, this is just a plot of the square root of the MSD as a function of the time or the space, and as you can see, for low density we just gain a straight line, meaning we have a free diffusion. Not surprising, everything is known. The second case, the second extreme, is the extreme of high density. In this case, we know that we are constricted to the origin, and in this case, as you can see from the plot on the left, we saturate to some saturation level. I think what is beautiful in this model is that we have a sharp transition between the constraint dynamics to the free diffusion dynamics, and it occurs at a critical density given in here. For those of you who are familiar with percolation theory, you can recognize that this is just the complementary density to the percolation threshold, the well-known percolation threshold. And why is it just the complementary density? Is that because in percolation theory we assume that the density is with regard to the number of available and unoccupied sites. However, in my model, which I'm going to show you in a second, I refer to the density as the density of the occupied sites, so the unavailable sites. So this is why we have this complementary. Okay, so this is the model, and the basic assumption of this model is that our random walker is significantly smaller than the obstacles occupying the arena. Why is that? Well, I showed you that there are no interactions in the model between the obstacles and the ant, meaning that the obstacles in this model are static. So this can only be achieved when we have a really small ant. However, this assumption is not valid when we consider random walkers which are on the same length scale of the obstacles, and in this case we should assume that the obstacles are in fact mobile. So this is, I think, the basic motivation of why to account for mobile obstacles, and if you are not convinced by that, let me just show you a video from an experiment conducted in the group of Professor Yael Roichman from Tel Aviv University. Here you see a random walker, or a robotic random walker, walking around in an arena filled with cubes, and as you can see, this random walker actually pushes boxes away or obstacles away, and in this model, or in this system, we cannot use the Antin-Labernev model to try and calculate the MSD, because as you can see, there are interactions. So to account for these interactions, let me introduce the Sokoban random walk. So what is the Sokoban random walk? And here is just a simulation of this walk. We have three basic rules. The first rule is the same rule as we had in the Antin-Labernev model. We can always hop into an unoccupied site, which is pretty simple, right? The second law, this is the part where we introduce the interactions with the between the tracer and the media. As you can see, now I can also hop into an occupied site as long as the next site is unoccupied. And in this case, what do? We just push the box or the obstacle one site forward. Note that this is not possible in case we have two obstacles just joined together. So this is the model, and now you maybe ask yourself, why do you call it the Sokoban? Well, this is just an homage to a well-known video game from the 80s, a Japanese video game called Sokoban. You see, these are the same rules basically. So I'm using video games on my job. Nice. So this is the model. And now I need to try and convince you that there is a significance to the introduction of these interactions. And how do I do that? Let's compare on the MSD level the Sokoban random walk and the simple random walk, or the anti-Labyrinth model. And we start with densities above the percolation threshold. So here are results taken from a numerical simulation. All I do, let's take a look on the plot on the left. All I do is to calculate the MSD. This is just an ensemble average, and I plot it as a function of time, or the steps, for both the simple, the anti-Labyrinth, and the Sokoban random walk for 3 densities, which all are above the critical density. And as you can see, both models attain a saturation level, which is finite, meaning that they are getting confined. This is not surprising because this is a well-known result for the anti-Labyrinth. But what I want you to note is that the Sokoban, for any given density, is actually attaining a higher saturation level, meaning that the Sokoban actually ventures farther away from the origin compared to the simple random walk. And I think that if you look on the right, this is just an example for just through one realization or one trajectory of a Sokoban random walk plotted on a simple random walk, and you can see how it illustrates the results that the Sokoban ventures farther away. So I think now it's the point in the talk that you look at me and you ask, why do you give this talk? Because this is pretty obvious, right? If I can push boxes or push obstacles from my way, I can venture farther away, right? So it's not really interesting, right? It's not surprising. You could have thought about it yourself. So the point is, in order to, say such a bold claim, we also need to check what happens below the percolation threshold. So this is what I did in here. Now I'm going to show you trajectories of a Sokoban random walk for a density of 0.4, which is below the percolation threshold. So here is the trajectory after 10 to the power of 5 steps, 10 to the power of 6, 10 to the power of 7, and I think, first of all, this is really beautiful, and you also see the evolution in time, okay? But now I'm going to show you what happens after 10 to the power of 8 steps. Long animation. So yeah, now you can see that these two images look identical, and it is not like they only look identical, they are identical. So on the left hand side you see the trajectory or the visited sites of a Sokoban random walker after 10 to the power of 7 steps, and then you see the same trajectory just after 10 to the power of 8 steps. And if there is no change in the trajectory, it means that our random walker in this specific realization is constricted, okay? So once again, you may look at me and say, okay, this is just one realization, this may be just a fluke. You cannot say anything from one single trajectory about the whole MSD or the ensemble average, right? You need to calculate or to look at the ensemble average as a whole. So this is what I did. So here I'm going to show you numerical simulation for the MSD, or the square root MSD of a simple random walk and a Sokoban random walk. And look and behold, this is what is going on. 3 things to look at. First of all, here I'm plotting the square root MSD as a function of the density, the initial density of the obstacles. And as you can see that for densities above the percolation threshold, what we get, as we've seen before, is that the simple random walk, or basically the Sokoban random walk, outperforms the simple one, or the anti-Labyrinth model, in terms of the MSD. I actually ventures farther away, and we've seen it. Second of all, I want you to know that when we approach the percolation threshold, the simple random walk, or the anti-Labyrinth, is approaching infinity, and this is not surprising thanks to the Gen, right? The surprising part, and this is where I come, is the fact that below the percolation threshold, while the simple random walk is at infinity, the Sokoban random walk actually attains a finite MSD. What does it mean? It means that for any given density in here, the Sokoban random walk is end up constrained in a finite cage, which is surprising because looking just at the densities above percolation threshold, we did not expect it, right? We thought we will get a higher critical density compared to the simple random walk. Okay, so now we need to explain the results, and this is where I pay another homage now to Dejean, who was an expert on scaling theory, and I'm going to use a scaling approach to solve this problem and calculate this square root MSD. And how do I do that? First, we need to understand what is going to be the jamming condition. We realize that the Sokoban is going to end up constrained. Now we need to figure out what is the condition for this jamming or constraint. So let's take a look at the following simulation. Again, a simulation of a Sokoban random walk pushes things away. In blue, I just color the trajectory. And in a second, you're going to see how this Sokoban random walk is going to cage itself in a finite cage. And I want you to look at it and think whether you can come up with some sufficient condition for the caging of this random walker. Just a hint, look at the depth of the layer that is constraining the random walker. A hint, it's not a single layer, but a double layer. So we are going to use now this knowledge in order to derive the condition, the jamming condition. So on the left, this is the configuration I've shown you before. On the right is the same configuration, but now I mark in green the perimeter of this wall. So let me explain. In purple, this is just the trajectory itself. In green, it's the perimeter of this trajectory, but it's not a single layer perimeter, but a double layer perimeter. Why do we need this double layer perimeter? Because if we have only one layer perimeter, the random walker can just push the layer forward and keep on moving on, right? So there's no jamming. I can still move forward. That's why we need a double layer perimeter in order to get jammed. So this is the realization. How do we write it down? So this is the condition, and I will explain. So think about the configuration on the right, but now we need to think about what does it look like at time 0. So at time 0, we have number of obstacles inside my area, which is just the size of my area, times the density, the initial density, right? This is the number of boxes. How do I get stuck? I need to take all the mass from inside the area and push it outwards towards the perimeter. When I do that, and I fill all the empty sides on the perimeter, which is just the perimeter times 1 minus rho, because I want them empty. So when I fill all the gaps, I create a double layer from which I cannot penetrate and get farther away. So this is the condition. How do we utilize it? This is very simple. So just for convenience, let me just denote R infinity is just the limit or the saturation level of the MSD, of the square root of the MSD. And this is just a one-dimensional scale of our configuration. Now what I do, I want to understand how both the area and the perimeter scale. So here from the simulation, I plot the mean area and the mean parameter for the ensemble as a function of this rho R infinity. And as you can see, these the dots are taken from simulation. As you can see, they follow a nice power law. So I can write this power law for the mean area and mean perimeter. I can get from the data, I can fit them into a linear line, and I can get the following values for alpha, beta, A, and B. And as I want you to note, we get powers which are non-integer, meaning that we end up with an area and a perimeter which are of fractals. So let's finish the calculation. So now we take our condition, we substitute the scaling laws, and we get the following formula. And this explains beautifully the result, because as you can see now, R infinity, the MSD, is explained by the initial density and by two parameters, C and gamma, which are given by the scaling lows. So as you can see, for any density larger than 0, we always end up with R infinity, which is finite, meaning that we are stuck in a confinement, which is very surprising, but also explains beautifully the results. Let me just finish in a second. So we just take the parameters that I've showed you how we get, I plug them in, and now I plot them together with the numerical results. And this is what we get. So here in dashed line I get this scaling. This is the scaling that I've just shown you. And in yellow you've seen this is a simple random walk, and in purple this is the Sokoban random walk. You see there is a great match between the scaling law I've gave you and the numerical results, which are independent. And I also want you to know that in grade area here, this is just a margin of 5% error. So from the dashed line upwards, it's just an overestimation of the parameters by 2.5%, and below it's an underestimation of 2.5%. And as you can see, the data falls beautifully inside this 5% margin. And just to sum everything up, today I showed you that short-range tracer media interactions are often neglected by people because they believe that they are not significant to transport properties. However, I hope that I was able to convince you that even if we introduce very weak interactions into our model between the tracer and the media, we get a totally different behavior. Above percolation threshold, we get that the Sokoban random walk ventures farther away compared to a simple random walker. And below the percolation threshold, everything changes. The simple random walker has a critical behavior, while the Sokoban random walker will always end up confined, which is really surprising. If you want to read this manuscript with all the results, all the figures, and much more, this is the archive submission, hopefully to be published very soon. And if you want to play the game, you can find it in here. And thank you for your listening.
Thanks. We have time for a few questions.
So if you can go back to your few slides, and when you're comparing your data with this one.
Yes.
So this shaded area is somehow your data falls always below this dotted line. Is there some reason for that? Is there some systematic error that is creeping in?
Okay, this is a good question. I mean, we are trying to figure out the point. I don't think I still have a concise an answer to it. I figure that it comes from the fact that we need to get even lower densities in order to catch the fractal the fractal dimensions correctly. The problem with going beyond 0.33, for example, is that you need to simulate the Sokoban random walk on matrices which are of size of 1,000 over 100,000 over 100,000, and you need to do it for at least 10,000 matrices. So we have two supercomputers in the lab, and they work non-stop on this simulation, because unlike percolation, you cannot run it deterministically. You have to run it in real time.
Yeah, I have one more question. So let's say if you have these obstacles, and does obstacle shape matters? Because in reality, let's say if you have a square versus circular obstacle, and then if you have a particle which is scattering through, you can get into a stage where, for example, square can lead to some sort of a bound orbit, where it doesn't basically pass through, it won't diffuse anymore. And for the circle, it will diffuse always. So it depends. So basically, the obstacle surface, whether it's flat or carved.
Okay. So this is a really good question again. Again, this is, I think we've sent it to review just 2 months ago, so everything is still fresh. But regarding to your question, we did try different geometries. We tried triangles, and we tried hexagonals. We see the same results over there. We did not try circles. We should try, you are correct. We also tried, I didn't have time to talk about it today, we also tried Cayley trees, for those of you who know Cayley trees, because percolation is exactly solvable on this topology. It turns out that the Sokoban is also exactly solvable in this case, and there's another surprise. invite me to another talk. We can talk about it then.
Yeah, I have just two short questions. So,
yes.
What is the scale over which things need to be pushed to get jammed? So basically, you showed us the scheme. I mean, some picture, no? That.
Yeah. So I think the figure you're looking for.
No.
Just a sec. I think this one will because.
Okay.
You see that it's around. For density of 0.45, it's around 10 to the power of 5.
So it should scale with the obstacle density, no?
It should scale, yeah, and this is what you've seen in the last, okay. So this is basically the scaling law that we got. This is the answer. You see that we only depend on the initial density of the obstacles, and these two parameters which just come from the power law scaling of the area and perimeter.
And what happens if you change the rules of the game? I mean, you have shown us a specific rule.
Okay, so I think the only rule that constrains us right now is just the number of obstacles that you can push at a time, because if you think about the Gen model, basically there you can just walk onto empty sites, right? Here you can also do another thing. The next level will be pushing 2 boxes at a time, 3 boxes at a time, etc., etc. We did not try that yet, on a full scale. But from the preliminary results we get, we see the same. We see the same behavior. I believe that we will get the same result, but now the powers will be a little bit different, and the scaling will be different. But this is going to be of the same functional form, I believe. But we should still check it.
Hi, very fascinating work. I have two questions basically. One is a follow-up to Pinaki's question also. But before that, you do not implement periodic boundary conditions in this, right? Because in the Sokoban game, there is no PBC.
So to answer this question, it's not because of the game.
No, I mean, yeah, of course.
But no, we're doing serious physics in here. No, I did. What we did in here, well, when you work with the percolating system, in order to get the critical density, the right evaluation, what you need to do is to look at the very large systems in order for the random walker not to run away out of the system. So you need to simulate very large systems. So when you do absorbing a boundary, it may be a solution which can save the data, but we wanted to start, first of all, with comparing to the most basic model, which is this 50 years old anti-Labyrinth model. But this is also a good point, what happens in a periodic boundary. I don't know how it is going to compare.
Right. And just a follow-up to that jamming question, what happens when a particle, when it walks into this, say, environment where it can no longer push around? Does it just walk back to where it came from? So is your walk self-avoiding, or can it just hover in that spot for a few steps, or must it come back immediately afterwards?
Okay, so this is also a good point. Thank you for mentioning it. So each and every time step, I need to decide on which direction I'm going to. I will always make a step. At each and every time step, I will make a step, and of course, I will only make the legal step. So, and if you think about it, there's no scenario in which I cannot take even one legal step.
So, so if there is no other step to go around, it will just follow back where it came from?
Yeah, because this is for sure will always be the possible step, right? I can always go.
But then you don't associate any kind of time scaling to this process. Like it could take, like in real time, it could be a longer duration than what it came back from. Because ideally if something goes into a trap, it will interact with the environment and like to be there because it's probably the most energetically favorable state. In that sense, I was asking actually.
Yeah, so in this sense, we really use just real time, and we didn't try to scale it. Maybe it's also a good idea. But
I would like to ask more questions, but maybe later.
Sure.
Any other?
So in the game that you showed, there were some immovable boxes also, and there were some movable boxes. Have you tried them with some kind of a relative density between these ant in a labyrinth and your movable boxes?
Okay, now it's not working, but okay. So here you said that there are cases which the boxes are not movable, right?
Yes,
so
like the walls.
Yeah, so it happens also in the simulation, right? There will be scenarios in which I cannot push any boxes around. So, can you take?
Like an immovable box.
So you say a priori, I'll just say, okay, this one is immovable. Okay, guys, this is an amazing question. I didn't have time to look at everything, but it should also be interesting because by doing that you can actually direct the random walker in a certain direction. And if you remember this guy, you see that when it walks around, it creates tunnels which sometimes are indestructible or very hard to destroy. So I believe it will go on the same line as this guy, that you create you just create some kind of tunneling, and which directs you in some direction. But we should also look at that as well. Thanks.
Any other? So, can I ask a question?
Yeah, sure.
Yeah, so you mentioned that close to jamming you have this two-layer structure. So it's not clear to me like why, because I thought that depending on that environment there can be 3-4 layer also, right? 3 layer also.
Yeah.
Most of them I agree will be 2 layer, but.
So what we did here is to just try to come up with a sufficient condition. Of course, that if I have 3 or 4 or 5 or 20 layers, I for sure cannot run away.
No, so I'm not talking about the rules. So I'm talking about that final structure that you get.
Yeah. So the point there is that because I can push one box at a time, the least restrictive condition for which I'll for sure be jammed is a 2-layer. I need to create a 2-layer, right? So you wanted to come up with a sufficient condition. Of course, it's a stronger condition. You can come up with other conditions which are more case specific, but we try to make sure that we demand the minimum, but we make sure that we are stuck. Yeah, basically, but you can also require more and more levels, that's true. Yeah, this is in 2D.
So things change in 3D, I suppose.
We have 3D. Again, not much time, but we have 3D. Different things happen in 3D. Again, every topology we get different results, which is quite amazing. I won't spoil you what happens in 3D, but something a little bit different. The dynamics are different because of the fact that the walk is not recurrent in 3D. So part of the fact that you jam yourself is that you need to return to the same place every time and push another box and another box to create this confinement, right? But in 3D, because you're not recurrent, you can just get lost and forget about the confinement that you created, and you just move away. But so there, the dynamics is a little bit different. Hope to finalize this part as well.
Okay, so let's thank the speaker once again.
Thank you.
Hello. Yeah. So let's thank all the speakers of the session and also Chair Shantan for doing a fantastic job. So just a reminder for today evening, as I wrote in the email, please be there on the other side at 7:15 so that we can walk to the, couple of buildings away at 7:30. Make sure badges, please.